Okay, welcome back. This is 4.4, concavity in the second derivative. So what's going to happen here is we're going to now do essentially the same thing that we did with the first derivative, but with the second derivative. Okay, so you'll obtain the second derivative, set it equal to 0, find the places where it's equal to 0 or undefined, and then those will be special places called inflection points this time, as opposed to maxes and mins, potentially maxes and mins. They were called critical numbers last time, right? So but I mean, really, it's the same game as the first derivative. It's just you're doing the same thing, but with the second derivative, okay? Okay, so what is concavity? It's a way of characterizing the shape of a graph. Okay, so the first derivative tells you whether the graph is going up or down. Concavity is telling you, is it bowl-shaped or is it upward bowl-shaped or downward bowl-shaped? Okay, so first, some definitions then of concavity. Concave up. So the shape is like a happy face. And so an ultimate example is any quadratic that you've dealt with where the leading coefficient is positive. So 5x squared plus 6x plus 3. Its first derivative, y prime, is 10x plus 6. Its second derivative is 10. Okay, so if that second derivative is positive, and here it's always positive, it'll be concave up. In particular, in this case, it's concave up on all of its domain. Okay. Another way to think of it is that the value of the slope of the tangent line is increasing. Right? So if you think of the slopes of the tangent line as a rate of change, f double prime of x being greater than 0, which is indicating concave up, this means that the rate of change of the slopes is increasing. Okay, so what does that mean? As I go across my graph, the little slope tick marks on the curve are going to be going up. Okay, so maybe this slope is negative 2, maybe the slope is negative 1/2, and then it'll go positive and then positive again. And overall, you'll have this U-shaped resulting. Okay? When the slopes of the tangent lines are increasing, in other words, when the second derivative is greater than 0, the little tangent lines will be kind of turning up. Okay, so they'll be going down at first and then moving in that direction with regards to time. Okay, so concave down then is the reverse thing. The concave down form looks like this, and that happens when the rate of the change of the tangent lines is less than 0. Okay, so as you go across your graph, you're going to see that the tangent lines to the curve will decrease. So if I start with maybe a slope of 2, at the next point, the slope would be going down a little bit. So maybe here the slope is 1/2, and then the slope will be maybe negative. So the end result of your graph will be this kind of U-shaped, downward shaped. So it's downward shaped. So if the first tangent line, maybe the slope is 1/2. Here, maybe the slope is a little less, right? So maybe the slope is 1/4. And then finally, over here, the slope is negative 1 or something like that. You see the slopes are decreasing. The rate of change of the slopes is negative. So when you have the second derivative, the rate of change of the slope being less than 0, that implies you have this concave down form. And an ultimate example then, of course, if you have a negative leading coefficient on your parabola, that indicates a sad face, right? So y prime here would be negative 6x plus 6, and then y double prime is just negative 6. So the second derivative less than 0 implies that we have a sad face. It's concave down. Okay, okay. But that's the idea. So we'll be interested in finding intervals in concavity. For us in the beginning, it's going to tell us the overall shape of graphs, so we don't need our graphing calculators to worry about this. Later on, concavity in 3 dimensions will be a little bit more complicated and not as straightforward. But we have a test for concavity, just like we had a test for increasing and decreasing, just the first derivative test. Test for concavity. So it's theorem 4.7 in particular. Let f be a function whose second derivative exists on an open interval. So I guess this isn't, the first derivative test is really about, I believe it was about finding maxes and mins, right? So this is more or less just a definition that we'll use. It was theorem 4.5 as the corresponding theorem for first derivatives. This wouldn't be like the first derivative test. Okay. No. So we'll have. Okay. Let me just write it down. So let f be a function whose second derivative exists on an open interval I. And basically, it just recaps what I said above. If the second derivative of x is greater than 0, then you have a happy face. Secondly, if f double prime of x is less than 0, you have a sad face. So it's, if you want to make a relationship between this and the derivative, with the derivative, this kind of statement, the first derivative, we were worried about, is it going up or is it going down? Is it increasing or decreasing or staying constant? The second derivative is all about kind of the shape. Is it concave up or is it concave down? Okay. So let's look at an example. Here we got example 1 from the book. F of x equals e to the negative x squared over 2. We want to determine the intervals where the thing is concave up and concave down. Okay, so I'm going to do a number line just like I did with the first derivative. So I'll need this second derivative first off. The derivative, the exponential, you always just get the exponential right back. But in this case, you have to multiply by the derivative of the guts. So that'd be negative 2x all over 2, which is just negative x. Okay? So negative x e to the negative x squared over 2. Then the second derivative, f double prime of x, will be, I need a product rule. Right? So leave negative x alone, and then I'll have e to the negative x squared all over 2 times negative x again. And then plus the derivative of negative x is negative 1, e to the negative x squared over 2. Multiply this out, and negative times negative is positive x squared, e to the negative x squared over 2. And then minus e to the negative x squared over 2. I need to, basically, I want to set this thing equal to 0 and plot it on a number line, and then determine if it's concave up or concave down on the intervals in between the places where these things are equal to 0. Where this thing is equal to 0, we'll call those inflection points. So before we were calling them critical numbers, now they're going to be called inflection points. Okay, so I set it equal to 0. I'm going to factor out the exponential part. You end up with x squared minus 1 inside here. You can set this part equal to 0. You won't get any information from that, though, right? Because an exponential will never equal 0. So this is kind of just thrown in the trash. And then x squared minus 1 set equal to 0. That does give you 2 answers, right? That's x equals plus or minus 1 when all is said and done. Okay, so I do a number line for the second derivative. I'm going to smoosh it in over here. You may want to label it. This is f double prime of x. We have to smush that in as well. You're labeling these guys, which will be inflection points. So you have one at -1, one at 1. Okay. And then I need to do my test value, my signs, and my conclusions. Okay, so test values, I'll try x is -2. Plugging that into here, this portion will be positive, but this will be -2 squared is +4 minus 1, that's positive. So the sign is positive, and my conclusion then is it's a happy face. Okay? So the slope of the rate of change of the tangent lines is positive, and you can kind of see, okay, it results in a happy face. Okay, let's try x equals 0. Plugging 0 into here now, it's negative, so it's concave down. And then finally, plugging x equals maybe 5 into here, 25 minus 1 is positive, so that would be happy face, concave up. Okay, okay. So let's talk then more about these particular values here, where the second derivative is equal to 0. Before, what did we have? We had critical numbers. Critical numbers happen where the first derivative is equal to 0 or the first derivative is undefined. And in addition to that, the function needs to be defined at that point. Okay? Here, we'll have points of inflections, which have pretty much the same kind of definition. The function needs to be defined there. And then either one of these two facts, either first f double prime of c is equal to 0, or secondly, f double prime of c is not defined. Then the thing is, then you have an inflection point, okay, at that point. In practice, we're not going to be too worried about these sort of minute details. When we go to our number line, it turns out that even if f is not defined, we're going to be labeling it. And it's because you can have certain cases, like the most obvious case is the rational function y equals 1 over x. This thing is not defined at x equals 0, but there's a change in concavity going from this interval to this interval. And we would want to know that fact. Okay? But this will not be a point of inflection, right? X equals 0 is not an inflection point, because the thing isn't defined there. But there is a change in concavity. It's going concave down, the concave up. Right, so we're going to be still considering that when we go to our number line, but technically it's not an inflection point. The inflection points will be cases where you kind of have an S shape resulting. So what does that look like? Here's concave down, and then it starts going concave up, right? So when it travels from concave down to concave up, that's when you have an inflection point. So here, C comma f of c is an inflection point. And it results in this S kind of figure. So in the other direction, maybe we have something like this. There would be an inflection, it's going concave up, and then it starts going concave down. Okay, so at this point, f of c is an inflection point. Okay, so the deal is when you're looking for these inflection points, you're going to find the second derivative, set it equal to 0, find where it's equal to 0 and where it's not defined. And then you're going to label those on your number line. And for me, it's good enough just to note the concavity. Right? I'm not going to be too worried about the inflection points until maybe we get the graphing. Okay? So like a quiz for now, just labeling the concavity, the intervals concavity is good enough. In this example here, I'll go ahead and do the whole 9 yards. But all right, so find the inflection points and note the concavity. Alrighty. The function f of x is sine of x over 2, and we're restricted to the interval from 0 to 4 pi. Alrighty then, I need to know the second derivative. F prime of x is equal to cosine of x over 2 times the derivative of x over 2, which is 1/2. And then f double prime of x is going to be negative 1/2 sine of x over 2 times 1/2 again. So that'd be 1/4 sine of x over 2. Okay, I need my inflection points. This thing is continuous, so I don't have to worry about the places where the second derivative does not exist. There are none of those places. I just have to set it equal to 0. So negative 1/4 sine of x over 2 equals 0. Multiply both sides by negative 4. You get sine of x over 2 is 0. And then you're looking for all the places where the sine of x over 2 is equal to 0. Okay? So on the interval from 0 to 4 pi, the angle that will result in sine being 0 will be what? 0, pi, 2 pi, 3 pi, 4 pi. Okay, so 0, pi, 2 pi, 3 pi, 4 pi. If I divide these by, or multiply these by 2, then I get x equaling 0, 2 pi, 4 pi, and 6 pi, and then 8 pi. So it's really not a matter of looking at all of these. You really only need to look at these two particular guys, 0 and 2 pi. These aren't in our domain. Oops, 4 pi is, sorry. So just these three. So I'm going from 0 to 4 pi. The only ones that will make it work will be these three. So 6 pi is out of this guy. When you put 6 pi in here, you get something that's in this domain, but that's not what we're looking for, right? We're looking for the x values, not the x over 2 values that will be in this domain. No, okay. All right, so it's these three values that I need for my inflection points on my second derivative number line. So here we go. This is f double prime of x, and I'm going from 2 pi to, well, 0 to 4 pi. 0, 2 pi, and then 4 pi. I don't have to worry about anything outside of 0 and 4 pi. Those are not part of our domain, so I'm just worried about this interval and this interval. Alrighty then, so I need test values, signs, and conclusions. Okay. So you probably want to use something like x is pi over 2, or just, yeah, that'll work, pi over 2. And then x will say 3 pi in there. So when I put pi over 2 into the second derivative, I'll have negative 1/4 sine of pi over 4. Sine of pi over 4 is positive, times a negative is negative. So I conclude it's concave down. Okay. When I plug in 3 pi into the second derivative, I'll have negative 1/4 sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1, so it'll be negative times negative is positive, and it'll be concave up. Okay. So there's inflection point where it goes from concave down to concave up at x equals pi over 2. I'll just note that inflection point at 2 pi, comma, if I plug 2 pi into the original formula, it would be sine of 2 pi over 2, which is sine of pi, which is 0. Let's look at one more. So here's 31. We have y equals x minus ln of x. It has an implicitly defined domain from 0 to infinity because of the natural log. Remember, the natural log looks like this. So it's only defined from 0 to infinity. All right, let's get the second derivative. Y prime is 1 minus 1 over x. In other words, 1 minus x to the negative 1. Y double prime is then, well, the derivative of 1 is 0. The derivative of this, bring down negative 1, negative times negative is positive, x to the negative 2. So 1 over x squared. Okay, the only potential inflection point would have been at 0. So if you set 1 over x squared equal to 0, there is a place where the second derivative is not defined. So x equals 0 is a potential inflection point, but because it's not even, this function's not defined at that point, it's no longer an inflection point. But yeah, so we could pretty much just throw it out, and then this equation has no solutions. If you multiply both sides by x squared, you get 1 equals 0, which implies no solutions. Okay? So there's no inflection points here, but we still consider them the second derivative from 0 to infinity. So this is f prime of x. And you could do a test value, a sign, and a conclusion. So test value, let's try x is 1. So you'll have 1 minus, oops, second derivative, 1 all over 1 squared is positive. And so the conclusion is it's concave up on all of its domain. So it's always concave up. This kind of makes sense. The original function is of the ln is always concave down. Then if you make it negative ln of x, it'll flip it about this line y equals, or sorry, it'll flip it around the x-axis, and you would get this, okay, which is concave down. And then if you just add in x at every point, it's going to make it go more like this, I suppose. So yeah, I mean it's concave up all the time, I think. Anyways, let's look at the second derivative test, which is like the first derivative test. We won't use it very much, but it's just a different way of finding mins and maxes. Okay, so you can always just use the first derivative test in order to get this done, but maybe if you're in a hurry, and also in Calc 3, you have to use the second derivative test, it seems. You won't be able to use a first derivative test, I think. I don't remember. Anyways, theorem 4.9 goes like this. Let f be a function such that f prime of c is equal to 0. And the second derivative exists, the second derivative of f exists on an open interval containing c. Okay, so the deal is, if you know that f prime of c is equal to 0, and f is defined there, then you know it's a critical value. Okay, it's one of our critical values. So if the derivative, the sign of the derivative is going up and then down, we would expect this thing by the first derivative test to produce a maximum value. So this is a workaround of that case. You can just find kind of your critical values on your first derivative number line, and then look at the second derivative below it. So if the second derivative tells you that in this interval below it, it's concave up, that will imply that there exists a min at this particular critical value. Okay, so this then implies that that thing is a min. Okay? Likewise, if you have an interval with a critical number, and then you look below it at the second derivative, and you find that the second derivative is negative in that interval, it's concave down, so you would expect this guy to be a maximum. Okay, so that's really all this thing is saying. And obviously they state it a little more precisely in the book, but let's just leave it at that and move on to an example. So problem 39, we have f of x equaling x to the fourth minus 4x cubed plus 2. Okay? One thing that should be noted is if the derivative and the second derivative are both 0, in other words, you kind of have like a critical value and then an inflection point down here, then there's really nothing you can do, okay, except do the first derivative test. Okay, so you don't know if it's max or min when they're both f prime of this value c is equal to 0, and then f double prime of c is equal to 0. Okay, so let's take a look at this guy. I need this first derivative and the second derivative. First derivative, 4x cubed minus 12x squared. Set that equal to 0 for those critical values. I can factor out 4x squared. I get x minus 3. So we'll get x is 0 and then x is 3 for critical values. The second derivative then, f double prime of x will be 12x squared minus 24x. Right? Set that equal to 0 and factor, so I got 12x times x minus 2. So again, I got a critical value, or a potential inflection point of x equals 0, and then an inflection point at x equals 2. Okay, so looking at my number lines then, here's f prime of x. Critical values at 0 and 3, and then f double prime of x. I have an inflection, potential inflection, well, it's definitely an inflection point at 0, and then definitely also at 2. Okay. And supposedly, what this second derivative test is telling me is that I can figure out whether it's a max or a min, so long as these aren't simultaneously 0. And so in this case, I cannot figure out if 0 is a max or a min because of that. Because they're both equal to 0, the first and second derivative are equal to 0 at that particular point. That's this case here. Okay. But I can figure out if this guy, F3, is a max or a min by looking at the concavity on this interval. Okay. So you do a test value, a sign, and conclusion. And so test value, we'll try x is 3. The sign of the derivative at 3 is positive times positive, positive. So it's concave up. And that then implies that there's a relative min at 3. Okay, so this implies relative min at 3 comma whatever it is. If you plug 3 back into the original function, you're going to end up getting negative 25. Okay. To figure out then if this guy is a max or a min, you would have to go back to the first derivative and then do your test sign conclusion here. And if you do that, let's say x is -1 and then x is 1. I'm plopping these into my first derivative here. So I have -1 squared is positive, -1 is negative, positive times negative is negative. And then for x equals 1, I have positive times a negative again, which is negative. Okay. So in this case, it's neither a max or a min actually at this point. So not a max or min at 0, 2. Okay, so I mean, that's the second derivative test. In general, I don't use the second derivative test very often, only in really the homework. I think the importance of the second derivative test is this kind of logical deduction that if it's concave up and there's a critical number above it, then that must imply that this critical number is falling in the valley. It's a minimum. Okay? That kind of logic could help you, maybe, maybe not, once you get into higher dimensions and start worrying about how things are going to work there. Maybe not. All right, so that anyways, is that it? Yeah, that's pretty much it. We'll adjourn. Thanks for watching.